This lecture is on climate change, part 2. So how do we know our climate is changing? Well, in 1988, the United Nations and the World Meteorological Organization created the International Panel on Climate Change, or IPCC. Some people call this the largest research project in history. The Intergovernmental Panel on Climate Change consists of over 500 lead scientific authors. There are over 2,000 scientific reviewers. And what this group does is it publishes a consensus of the scientific climate research from around the world. It summarizes thousands of studies. It documents trends in surface water, temperature, precipitation patterns, sea level, storm intensity, etc. And it also predicts future changes in our climate. And finally, it discusses the possible strategies to pursue in response to climate change. So the IPCC has published several reports since its inception in 1988. The latest report was in 2014 and is called the Fifth Assessment Report. It's a comprehensive report of all of the information out there on climate change. Now, the sixth assessment will be finalized in 2022, when the countries who are part of the UN Framework Convention on Climate Change will review the progress that the world has made under the Paris Agreement. And the progress is towards the goal of keeping the average increase in global temperature to well below 2 degrees centigrade. So scientists had come to the conclusion that we cannot increase our overall average temperature above pre-industrial levels greater than 2 degrees centigrade, or it would have severe harmful effects on humans and the environment. So that was the goal they set at the Paris Agreement. Now, from 2018 to 2022, there will be 3 special reports released almost every year. And the first one of these was just released. The draft was released, and it's impacts of global warming of 1.5 degrees centigrade. So as you can see, the scientists have said we cannot go above an average increased temperature of 2 degrees centigrade, but we are already at 1.5 degrees centigrade. And so that is what this report is about. What are the impacts? The second report is expected to come out in August 2019, and this is going to be about climate change and land, mostly about desertification, which is how a lot of the planet is turning to deserts. And then the third report in September 2019 is about oceans and the climate change. So let's take a look at some of the conclusions of the fifth assessment, and we're going to look at this in a very simplistic way because there's a tremendous amount of data and information there. Now remember that these assessments of the IPCC are a rigorous review of the most current scientific data. And what it shows is that our climate is changing, that we are the cause, the impacts will become increasingly severe, and the impacts are occurring at a faster rate than previously predicted. The reports that have come out since this fifth assessment are just reinforcing the conclusions of it. And the thing that we want to keep in mind, too, is that there is strong scientific consensus that this is happening. We also should keep in mind that we currently have the means to limit the climate change and to build a more sustainable world. So what I'd like you to do now is take a look at this interesting graphics that was put together by Bloomberg, and it's based on data. Okay, so you can see here, the question is, what's really warming the world? And of course, there are a lot of skeptics that climate change is occurring and that it's causing these warmings and that man is the cause of it. So what Bloomberg Business did is they took the different causes and they showed the contributions of those causes to the increased climate change. So, you know, the first line that we have here shows the measured or observed land ocean temperatures. Okay, so here we've got this, and you can see that this is the average, and this is 2 degrees Fahrenheit above, 2 degrees Fahrenheit colder. And this is from 1880 to 2014. Okay, so let's scroll down. Now, one of the questions is, well, maybe the warming is because of a change in Earth's orbit. So remember we talked about the Milankovitch cycles and the fact that the Earth wobbles on its axis and its orbit changes. But these changes don't occur over tremendous time spans, like every 100,000 years, maybe its orbit changes. And that sometimes this can change the climate and push us into an ice age or out of an ice age. So maybe that's what's changing the overall average. But so what they do it is they added in the influence or the impact of temperature from orbital changes. And so what you see is a blue line here, and around the blue line is actually the range of temperatures that would occur due to changes in Earth's orbit. Okay, so what they're saying here is this is what our average Earth temperature is, but this is where it would be if our orbit and the tilt was contributing towards an increase in global temperature. So obviously it's not, because the temperature would be lower than it actually is, so it can't be that. Well, what about the sun? Some people say, well, the sun's temperature varies over decades and centuries, and this can have an effect on our climate. But again, what they did is they put in here what the temperatures would be on Earth just based on the changes in the sun's energy, and you can see again, the average temperature, this orange line, is well below what the actual average temperature is. So it can't be the sun either. And they said, well, maybe volcanoes, because there's some data that show that, volcanoes emit 100 times more CO2. Volcanoes emit a lot of CO2, and maybe that's causing the warming. But again, if you look at the red line, you can see in most cases, the Earth's average temperature should be lower than it is due to volcanoes. And the reason it isn't is because volcanoes actually cause cooling, and humans release 100 times more CO2 anyways than volcanic activity. So it's not volcanoes. Well, what about all three things together? So now we're combining them, and still we see that they cannot account for the change that we're seeing. So natural factors are not responsible for the increase in the average temperature in Earth's average temperature. So if it's not nature, is it deforestation? That's humans cutting down trees. Remember, trees absorb carbon dioxide, and if you cut them down, they don't absorb carbon dioxide, and that is a greenhouse gas. That could warm our climate. But even if we're just looking at cutting down trees, that again would not raise our average temperature as it is being raised. What about ozone pollution? Ozone pollution isn't doing it either. What about aerosol pollution? No, aerosol pollutions actually cool the planet. They don't increase the average temperature. What about greenhouse gases? So when you look at the impacts of greenhouse gases, it is quite clear, and if we really focus on CO2, that is the reason for the increase in temperature. So this is a really nice graphic that shows that. Okay. So let's continue on. How do we know our climate is changing? Well, there are really three major ways you can measure that. You can directly sample the atmosphere and look at the temperature level and the CO2 levels and other greenhouse gas levels. You can use proxy indicators, which means indirect sampling methods, perhaps for time when we didn't sample and humans weren't around. Maybe there's something else we could measure that carries information in it, kind of like skeletons in the rock, that can tell us what the climate was like in the past. And then climate models, which are computer programs. So let's look at an example of direct atmospheric sampling. And if you look at the x-axis on this graph, it has the years up to 2020. So obviously that sampling hasn't happened yet. And the x-axis is temperature deviations from the 1880 to the 1920 mean or average. So what this is measuring, this graph, is not the actual temperature, but how the temperature has changed from the average temperature before the Industrial Revolution. So 0 means it hasn't changed. 0.2 means it's gone up by 0.2 degrees. Minus 0.2 means it's gone down by 0.2 degrees. So the dots that you see here are actual measurements, and what they've done with the dots is they've taken them and put them into models. So the lines are predictions of the temperature by the models. So what you can see by this, what we see by these graphs, is that the average global temperature has gone up from the past. We can also see that the models are pretty accurately predicting what the data has already shown us. Okay, so this is an animation I'm going to show you that shows a change of Earth's average temperature from 1952 to 2013. And what I want you to notice is the colors. So the colors give a sense of the temperature changes over time. So if it's a lighter blue color, it's cooler. When it gets yellow, it's getting a little warmer, orangey warmer, brown really warm. So keep in mind, the darker the colors, the warmer the climate, and I want you to notice what's going on. So let's start this. So we can start with 1954. There's a lot of blue, there's some yellows, blues. 80s, we're in the 80s, we're seeing more yellows. 90s, we're seeing more oranges, darker oranges, and here we are in 2013. So if we go back to that for a minute, again, so what you notice is that over this time period, from the 50s to 2013, there's a lot more oranges. But I want you to notice where the darker colors appear. So let's watch that again. Okay, so you're noticing some of the dark colors are in the South Pole, the northern part of the country, and then we've got a lot of the darker colors are in the northern part. So what appears to be happening here is that the world as a whole is warming, but the poles, the Arctic and the Antarctic, are warming a lot faster. Here's some more data. This is some recent data from a group collecting climate data called Climate Central, but the source of the data is NASA and NOAA. And so you'll notice that the 10 hottest years globally on record were the last couple of years here. And so this is on record, and they're showing you the temperature anomaly, which means the average increase over the Earth's temperature. So the last 10 years have been the hottest on record, and 2013 was the third hottest year on record without El Nino. El Nino is a phenomena that happens in the oceans that causes the climate to warm, and it's a natural phenomena. So it comes and goes, but they're saying even without an El Nino, this was the third hottest year on record. So Earth's average temperature has increased by 1.6 degrees Fahrenheit. Oops, sorry about that. 1.6 degrees Fahrenheit over the last 100 years. Now remember, again, to keep in mind that typically what we see in temperature changes between glacial and interglacial periods is an increase by 0.08 degrees Fahrenheit. So when we're looking at interglacial periods, meaning when there's no glaciers on the Earth, and glacial periods when there is glaciers on the Earth, the average change in temperature is 0.08 degrees Fahrenheit. That's an 08. And this happens, over long periods of time. So we're seeing an increase of 1.6, but even when you have the extremes of having glaciers and no glaciers, the average is 0.08. So this is fairly significant. Something is happening. In fact, the U.S. is warming very fast since the first Earth Day, which was 1970. But some states are warming at twice the global rate. So let's take a look at this. This is some more mapping from Climate Central. And this is a nice interactive map of the U.S. So if you look down here, it shows you the temperature change degree Fahrenheit per decade. So how much are these states warming per decade? And the yellow color means at the lower end, they're not warming a whole lot, 0.3. At the higher end, 0.7 degrees per every 10 years. So what you can do is you can run your cursor over it, and we'll take a look here at New Mexico. And you can see this, they're showing you the average increase in temperature. In fact, New Mexico is the fastest warming state in the U.S. They are warming at a rate of about 0.63 degrees Fahrenheit every 10 years. Close seconds, oops, get rid of this. So close seconds to New Mexico are Vermont, and Arizona, Delaware, and New York. So all of these states that I just mentioned are warming much faster than the global average. So when did we really start to be aware of this problem? Well, if you remember the video in which Katharine Hayhoe speaks a little bit about this, it was a long, long time ago. But I think when most American scientists became aware was with this individual whose name is Charles Keeling. Charles Keeling. So Charles Keeling was a graduate student in 1958, and he wasn't really sure what he wanted to do, so he started collecting carbon dioxide data on Mauna Loa on the Big Island of Hawaii. And you can see on the x-axis is the years. So he started in 1958, and the y-axis is the carbon dioxide concentration in parts per million per volume. So if we look at this graph, there's a couple things that you can note from it. First is that the CO2 levels are definitely increasing. Now, he didn't keep collecting this data for this long. His research was a short period of time, but after he made this discovery, other people came and manned the station, and they're still collecting this data today. So one thing you can tell from this graph is the CO2 level is rising. Another thing you can tell is that it seems like the CO2 level goes up and down every year, as we can see in this little blow up here. So it seems to go up and down every year. And then the last thing, or I guess the last question I would ask you is why does that happen? So one thing is, why do you think he chose Mauna Loa? Well, he was trying to look at the global levels of carbon dioxide. And Mauna Loa was far from cities. So it would be far from the pollution of cities, in which carbon dioxide was being produced. So he wanted a global average. He didn't want his data to be affected by some city nearby. And so he thought out at Mauna Loa, it was a lot safer. It was a lot further from inputs from the city. What does the graph tell you about CO2 levels? Well, they're increasing. Why does it go up and down? Well, if you think about it, in the spring and summer, the plants and the trees are growing, and they absorb the CO2 out of the air. And so the levels of CO2 in the atmosphere drop. So that's why it goes down in the spring and summer. However, if you look at the winter-fall, what happens is that the plants die. And as they do, they release the CO2 into the atmosphere. And so what happens is the CO2 level goes up. So that's kind of what's going on with the up and down. So Charles Keeling was one of the first people to measure this, where it really started to get noticed. Well, what else do we have for evidence? We have proxy indicators. This is indirect evidence that serves as a substitute for direct evidence. So in other words, it kind of sheds light on the past climate when people actually weren't sampling. What kind of evidence do we have? Well, we have these ice cores, and you can see an example of someone holding one in the upper right-hand corner. So if you go to parts of the world where it's been frozen for long periods of time, like the Arctic or the Antarctic, you can actually chisel down and take out a core, and that core contains, trapped in every level of it, little bits of the atmosphere in bubbles. And so, for example, if you went down 10 feet, that might be a sample from the atmosphere 300 or 400 years ago. And so that's kind of, this is some of the evidence they're getting. Now, in those little trap bubbles, you can tell the temperature that was in the air at the time that the snow fell. You can tell this actually by looking at ratios of oxygen isotopes. Colder temperatures have higher concentrations of the lighter oxygen isotopes. You can tell what the greenhouse gas concentrations were, CO2, sulfur dioxide. You can tell whether there was a lot of snowfall, whether there were fires and things like that. So there's a lot of information to be gotten from ice cores. There's also cores in sediment beds. For example, in the bottom of lakes, you can take a core just like an ice core. And in the sediment beds are pollen grains and other plant remnants that give you a lot of indication about weather, how much carbon was in the air, temperature. Tree rings indicate age, wetness of season, droughts, and seasonal growth. So even though you can't go as far back in time with tree rings as you can with ice cores, they're just another level of data to confirm what you're finding. And then coral reefs provide information on past ocean conditions. This is because coral build their shells out of calcium carbonate. Calcium carbonate is a chemical that has this formula. So what happens is the carbon dioxide gets into the water and it absorbs and gets turned into calcium carbonate. This contains oxygen isotopes as well as trace metals, and you can use this to determine the temperature of the water in which the coral grew. So let's look at an example of an ice core. Okay. So let's take a look at this. This is an example of an ice core from the Antarctica. It's called Dome C. So I'm going to write this here. This is from Antarctica. And this was drilled down about 10,728 feet. So this went down about 2.2 miles. So at the ice at the bottom of this was 800,000 years old. 800,000 years old. Okay, so on the x-axis we can see the present, which is time 0, all the way back to 800,000 years ago. And then we see three lines here. The black line is temperature, the average temperature change. The green line is the methane concentration. Methane is a very powerful greenhouse gas, and you'll notice its units is parts per billion. And then the red line is carbon dioxide levels, and you'll notice its concentration is parts per million. So the methane levels are much, much, much lower than the carbon dioxide levels. So if we look at this graph, it's showing us temperature and CO2 changes over time. Okay, it's showing us that. And so what can you see from this graph? What could you predict? Well, there's a lot of up and down. So the temperature seems to go up and down and up and down. But the same can be seen with the methane levels and the CO2 levels. In fact, it would seem like every time the CO2 level goes up and the methane level goes up, so does the temperature. And every time these levels go down, so does the temperature. In other words, the temperature and the CO2 and methane are correlated. That means they are related. They have a relationship with each other. So this is kind of important. It's clear that CO2 levels and methane levels are related to the temperature levels. And of course, now what we know this means is that when the carbon dioxide levels were the highest, the temperatures were the highest. When the carbon dioxide levels and methane levels were the lowest, the temperature of the Earth was the lowest. And by the way, this graph is showing you the major differences between glacial periods. So when the graph is low, the temperature was low, this is when the Earth was covered in glaciers. When it was high, this is when there were no glaciers. Okay? The other thing you can notice from this graph is that today, our CO2 levels they're actually above 400 now. They're higher than they have been in the last 800,000 years. And the methane level is higher than it's been in the last 800,000 years. So that's very powerful data to show us that the climate is changing. And it's changing in the way that it has never been changed before. If we go back to this slide, this is a graph that was constructed from data collected all over the world, CO2 data. And if you look on the right-hand side here, all of these are the data points. So this is where the data was collected. And up at the top, it gives you a little key. The red is Mauna Loa, which is where Charles Keeling started and is still being monitored. Now over here on the left, they're showing you the carbon dioxide level. So in the middle is the equator. And then here we've got 30 degrees north, 30 degrees south, 90 degrees north, 90 degrees south. So what they're going to do is plot the results of the data of the carbon dioxide level on the left and then show you the year on the right. So let's start with this. All right, so here's Mauna Loa red, here's Mauna Loa, the data point. Here is the South Pole, here is the South Pole data point. So we're in 1982 now, and as see 1983, so you'll notice it goes down and up, right? It goes down in the winter, up in the spring, down in the winter, up in the spring. Now we're in 1985, 86, 87, and you'll notice more data points, more people are collecting data on CO2 levels, up 1989. And you'll also notice this on the right here, the CO2 level is steadily climbing. You still have the up and down every semester, every year, but it's slowly climbing. 1993, okay, so we're adding more data points. You can see the CO2 level. This is the original level here. Keeps going up, and we're starting to get some real variations during the year. Now we're up to 370 parts per million. It's the year 2000. Keep going up. We're over 370. 2003. 2005, we're approaching 380 parts per billion. And we're getting close to 390. Now it's 2010. 2011, we're past 390. Okay, so let's stop this for a minute here. So we are past 390 parts per billion. It is January 2012. And now you're seeing they're adding some more data. And this is the Keeling data. So people are continuing to monitor. So let's see what happens. So we're adding the Keeling data from before, sorry. Okay, so this is the most recent data here. This is Keeling's data. Okay, and now we are adding data from an ice core, which goes back even further in time, all the way to pre-industrial levels when there's only 278 parts per million in the atmosphere. So this is from an ice core again. Okay, so you can see where we are today. And now we're going to add in data from another ice core, the Vostok ice core, which goes back even further, 20,000 years ago, 40,000 years ago, 50,000 years ago, 60, and now we're going back hundreds of thousands of years ago, again from the same ice core. And you're noticing now the levels are even lower. And now we have additional data from a different ice core, Antarctica. And you can see where we are. So this is 800,000 years of data of CO2 levels. And what's very clear from this is that the levels that we are at today are higher than they have ever been. Now remember, man only came along around here. Somewhere around here is when humans came along, maybe a little before that. And so that is one of the few variables that's different. Okay, so again, the data for the fact that the climate is changing is very, very powerful.